Hey there, AP Calc students. Lesson 3.4 is on tap for today, velocity and other rates of change. Here we'll be looking at some practical problems involving velocity and other things, as well as some particle problems, which are a classic part of calculus. So at this point, as you can see, we've really emphasized the fact that the derivative can be interpreted as the slope at a point, and we've really been focusing on that, and we've learned how to find derivatives the long, arduous way, and now we have also practiced the more shortcut way. So now it's time to look at some practicality of where derivatives might actually be used. So the key thing is remembering that a derivative is a rate of change, and there are many somewhat practical problems that involve rates of change, and that's what we'll be looking at in this lesson. So anyway, here's some classic examples where we'll see these types of problems, obviously with velocity and acceleration, those types of things, volume and area, how quickly those are changing when something on a particular shape is manipulated, and then even in economics we'll look at an example here of how we can use some calculus to solve a problem there. Alright, first of all, basic information that we'll refer to quite frequently, and this is generally referring to things that are in motion like projectiles and things like this. Those of you that are in physics or have had physics will recall several of these terms, and now we relate them to calculus. Usually if you're given a particular f of x or a particular y equals function, that's going to describe the position. In other words, how high a particular object is or something of that nature. So that's my initial function. Now if I take the derivative of that, that's going to represent the velocity, and usually the velocity at a particular point if we put in that particular x value. And we've mentioned this before, I think. Speed is not quite the same as velocity. Velocity has a direction in addition to a magnitude, but speed is always going to be considered non-negative. Then acceleration is considered to be the second derivative. So if I know the velocity, if I take the derivative of the velocity, that's going to give me my acceleration. So the rate of change of the velocity, in a sense. A couple other words we'll see quite frequently is displacement. Displacement, maybe a good way to think about that is just what's the change in y value. Typically from when you start to when you finish, you might travel quite a long distance, but just thinking about what's that change in y value from when you started to when you ended. And then of course average velocity would be again our change in y value, but then we'd have to consider our time in here as well. So change in y over the change in time would give us our average velocity. Alright, here's a pretty classic problem involving particles. What we mean by a particle, it's kind of moving back and forth, usually along a particular line, and this is going to give our position at any particular time, right here. And we can also try to find some things out about the velocity and acceleration as well. So we'll kind of go through this problem. This will give you a good example. This is going to be kind of screwy, I think, at first, but I think you'll catch on here eventually. So first of all, the displacement during the first 10 seconds. Again, we want to think of at time equals 0, where is this particle? So if I put a 0 in place of all of those t's in there, you see I'll get 0 minus 0. My answer will end up to be 3. So that means at 0 seconds this particle is at a position of 3, positive 3. Then if I think about where is my particle going to be at the second, so if I put a 2 there in place of all those t's, notice you'll get, I'll kind of write it in there, so it'll be 2 squared minus 4 times 2 plus 3, so that's 4 minus 8 is negative 4, and where am I doing this wrong? Yeah, and I do want it at 2 seconds. Yeah, so 4 minus 8 is negative 4, negative 4 plus 3 is negative 1. Alright, so what's my change there now? Well, from negative 1 to 3, and actually I better write it maybe like this, because at 2 seconds, I'm at -1, I better subtract my 3 here, and notice I get an answer of -4. So that's my displacement. So it's, in this particular example, we would say it's 4 units to the left, the negative there meaning the left, 4 units to the left of where it started. Kind of goofy, but just think about where it is when it starts, where it is when it finishes, subtract those two values. All right, what about average velocity? Like we talked about, during the first 5 seconds actually. So I'm going to say, if I put a 5 in there for my, actually, let me just back up here a little bit. When I'm talking about velocity, I can't use this same function right here, can I? Because velocity is that first derivative. So my first derivative here, and I'll write it like this.
Your attention, please. We would like all 9th grade band members to report to the gym at this time for the yearbook pictures. And just a reminder to students to watch the schedule and arrive on time. Thank you.
All right, there's a nice photo announcement there to break up your day here listening to me in the video. Anyway, so take the... no, I'm kind of goofed up here. That I don't want the average velocity here yet. Or I don't want the instantaneous velocity. I was thinking of that more for part C. So I'm going to make an erasure here. Sorry about that. My average velocity, I just want to consider what's my y value going to be at 5. So my s of 5, so that's going to be 25 minus 4 times 5 plus 3. And if I figure that out, that's going to be 25 minus 20 is 5. 5 plus 3 is 8. Okay, and then what's my s value at 0? Well, we already knew that. That was going to be 3. So then this is essentially going to be a change in y over change in x. So it's going to be 8 minus 3. And the first 5 seconds then I have to consider 0 to 5 is also 5. So 5 over 5 is 1. So the average velocity here is going to be 1, and I guess we're in meters here. So it'd be like 1 meter per second is my average velocity. All right, now I was kind of goofed up there a bit, but let's go down to letter C, the instantaneous velocity. Now the instantaneous velocity is where I want to take that first derivative. So when I find the derivative of this, now that we know our shortcut rules, we know it's going to be 2t minus 4. That's my derivative. And when t equals 4, simply all I have to do is put a 4 in place of t. And 2 times 4 is 8. 8 minus 4 is 4. And so my answer is 4 meters per second. Remember that velocity is the derivative of my original function, which describes position. All right, so far so good. Here's the last two parts of this. What about the acceleration of this particle when t equals 4? Well, acceleration, as we've learned, is not just the first derivative, but the second derivative. So my velocity here, I'll just rewrite this. My velocity was 2t minus 4. My acceleration then, I'll write it as a of t, is going to be the derivative of this. And this is going to end up to be just plain 2. Because the derivative of a constant, of course, is 0. So acceleration is 2. So when t equals 4, that is what you should get. It's a constant acceleration. Now, what values of t does the particle change direction? Now, this is a little bit tricky, but maybe we can illustrate it best with a graph, perhaps. If I went ahead and graphed my original function here, it would look something, I think, like this. Basically like that. That's my original function here. And remember, this is the position. This is the position. And when I think about changing direction, it has to do with velocity. So if I think about my velocity function, and remember this is what it is, I could graph that easy enough. I think I will here with a different color. Maybe I'll do that in red. 2t minus 4. So we would have a y-intercept of negative 4 and a slope of 2, so it looks something like this. Now, when it changes direction is when your velocity changes from negative to positive. So as I look at this red line that I drew here, this is my velocity. Underneath the x-axis, my velocity is negative. Above it, it's positive. So it's going to be right here where it changes direction. So basically what you can do is set that velocity equal to 0. 2t minus 4 equals 0. I'd add 4 to each side like this, and t is going to be 2. So at 2 seconds, that's going to be this spot right here, that's where that particle is going to change direction. Alright, kind of goofy, I know, but we're going to go on. You have this in your notes and you can ponder it later. Alright, here's another kind of famous graph here. I'm going to try to do a little graphing here and change my pen thickness. So I have to sketch this out a little bit. I have a point here and here and here, 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 and right there. So I'm going to connect these up. Now the difference here is that I have a velocity graph. So this graph is the v of t. So it's not the actual position, this is the velocity that's being graphed here. So we just want to analyze this. It's a little bit screwy, so here we go. The v of 2, well, this is the actual velocity here. So if I look at right here at 2, what is that particular y value? And sure enough, it is going to be negative 1. That's saying your velocity at 2 seconds is negative 1. Now, what about the acceleration at 2? That's what this letter here means, the acceleration. And now remember that acceleration is the derivative of velocity, and in a sense, graphing-wise, it means the slope. So what is the slope right here? What is the slope right here at 2? Well, it's a constant slope, it looks like, and I can tell it's going to be up 2 and over 4. So my answer here is actually going to be positive 1/2, because that's the slope of that particular line. Alright, when does this particle move to the right? Well, it moves to the right anytime that y is greater than or equal to 0. And so in this particular case, it's going to be between, when x is between negative 5 and negative 1, as you can see. And in other places when x is between 4 and 5. So it has to be graphed above the x-axis in order for this particle to be moving right. And then in similar fashion, of course, in order for it to move left, that's going to be when your y is less than or equal to 0. And so in this case, that happens when x is between negative 1 and 4. How many times does the particle change direction? Similar to what we saw last time, changing direction would mean changing from the positive to the negative. So it does only change direction twice, and that's at when t equals, looks like about negative 1, and t equals 4, because that's a place where it's going to cross the x-axis and change from being negative to positive. Alright, when is the particle at rest for more than a second? The answer there is never, because when it crosses from one to the other, it doesn't level out. It just stays there like that. Alright, really time for another slide, but we'll see. Average cost of producing 100 washing machines. Here's our economics lesson here. And this is the dollar cost of producing X washing machines. The average cost of producing 100 of these, well, I'd want to try to figure out what would my cost be of producing 100. So I would just put 100 in place of X like this. And when I do that, I would get a grand total of 11,000, like that. And then I know that I am producing 100 of those, so I'll just take 11,000 and divide by 100, and I end up with $110. Easy enough. And now here's where the calculus comes in, the marginal cost. Marginal cost can be considered a rate. So what's the rate going to be? In other words, the cost per machine when 100 machines are produced. So here's where I'm going to take now the derivative. Anytime we're talking about a rate, we're going to take the derivative. And my derivative for this particular function, now that we know our rules here, is going to be 100 minus 0.2x. And so if I now put 100 in place of x here, I am going to get 80. And that means my marginal cost when I'm producing at that 100 machine level is now going to be just $80 per machine. So that's where mass production makes some sense, because the cost for producing an extra machine now is going to be less than what it was for those first 100. All right, thanks for hanging in there, everybody. We'll be working on these kind of problems in class, of course, so we'll see you then.